Dear students, Assalamu alaikum wa rahmatullahi wa barakatuh. Today we will finish stereochemistry, which we started before the break, and we will show how we can present the chiral centers using Fischer projection. Usually, we can draw the chiral center in 3 dimensions by showing the atoms or the grooves, bold, dash, and lines. In Fischer projection, we switch to have the drawing showing two grooves in front, bold, and two grooves in the back or rear side. The one on the left side and the right side are front, and the one up and below are back. And we can just draw it as lines, which means always that the left and right are forward and the up and down are backward. As we see in this molecule, where we have four groups, the hydrogen and the OH. When you rotate it a little bit, they become front side, and the carboxylic acid and the methyl are rear side. So we can present them using the Fischer projection like this. For example, in this case, we have this compound. We have number 1 chlorine, number 3 methyl, number 2 propyl, and number 4 hydrogen. So now number 4 in the bottom, which means the rear side. So we can take the configuration. It is going from 1 to 2 to 3. This is R. The other isomers is this one here. This is the mirror image of this one. And you can see also number 4 here in the bottom, which is the rear side. So we can take the configuration from 1 to 2 to 3. This is S. But if number 4 is not in the top or in the bottom, like in this case, so we can make switching. This is the numbers we have, the priority numbers. The OH is number 1, 2 is the carboxylate, 3 is methyl, and 4 is hydrogen. So number 4 is not in the rare case, up or down. So we have to make a switch. Switch 4 with 2 or with 3, doesn't matter. You can put 4 here or you put 4 here. So we switch it with the 2 or 3. Now if you switch 4 with 2, then we have to switch 1 and 3. As you see here. So now 4 in the rear side, so we can take the configuration going from 1 to 2 to 3. That would be R. Okay. In all the previous exam, we show one chiral center, so we have one configuration R or S, and we have two isomers. The relationship between these two isomers were enantiomers. What about if we have more than one chiral centers? What kind of stereoisomer are we going to get? In this example, 2-bromo-3-chlorobutane, we have two chiral centers. This carbon is chiral and this carbon is chiral. So now, because we have two chiral centers, so we have the possibility of each one of them to be R or S. So there are 4 possibilities. Both of them are number 2R, number 3S, or number opposite, number 2S and number 3R, or both of them S. So we have 4 stereoisomers. In general, whenever we have more than one chiral center, we can predict the number of stereoisomers by using this formula, 2 to the power n, where n is the chiral centers. In this case, we have 2 to the power 2 is 4. If we have 3 chiral centers, then we have 2 to the power 3, that would be 8, and so on. So now what's the relationship between these two isomers? Let's draw them first, and then we can see what kind of relationship between them. These are the 4 stereoisomers. 1, both of them R, 2, both of them S, and this carbon R, this carbon S, and 3, or the opposite. This one is S, this one is R. So you can see that 1 and 2 are mirror images. 3 and 4 are mirror images. So by definition, any mirror images, stereoisomers, are enantiomers. So the relationship between 1 and 2 enantiomers, and between 3 and 4 also enantiomers. Now we will have another kind of stereoisomers called diastereomers, where they are stereoisomers that are not mirror images. So the relationship between 1 and 3, or 1 and 4, diastereomers. 2 with 3 or 2 with 4 are diastereomers because they are not mirror images. So now we introduce a new kind of stereoisomers called diastereomers. And the definition of diastereomers are stereoisomers that are not mirror images. What is the properties of diastereomers? We saw before that enantiomers are very similar. They have almost exactly similar chemical and physical properties, except one physical property is their interaction with a plane polarized light. The enantiomers, they interact with the plane of the polarized light and they rotate the light one to the left, one to the right. That's the only difference between them based on physical properties. In chemical properties, their interaction with another optically active or chiral compound would be a little bit different. I will discuss this later. But the stereomers, they have different physical and chemical properties. They have different melting point, boiling point, density, solubility, etc. You can work in this as example. This is glucose, which has, as you see here, 4 chiral centers, so you can predict the number of stereoisomers and the relationship between them, and try to draw all of them as practice for you. Two 3-dichlorobutane has 2 chiral carbons, and these carbons are very similar. They have the same groups. Each one of them has chloro, methyl, hydrogen, and the rest of the molecule. And now there are 4 possibilities for the R and S configuration. RR, both carbons are R, both are S, one of them R and one of them S. And now this is different than the previous case because the 2 carbons are the same. Then when the chiral centers have a configuration R and S, these two are identical. If you rotate one of them 180 degrees, it will be superimposed in the second one. So the 2 compounds look like mirror images, but they are superimposed, so they are identical. This kind of molecule is actually called Meso compound, which is a compound that contains more than one chiral center, but it has also plane of symmetry in this compound. It has a mirror in the middle of it. So this will reduce the number of stereoisomer to 3 instead of 4. So Meso compound now is new stereoisomers that is achiral, and it is the stereomers of the other two, the stereomers of the RR and SS configuration. Tartaric acid is another example. It's very similar to the previous one. Also, it has 2 chiral centers, which kind of identical. So we expect here to have also a meso compound, and you can see the relationship between these compounds. The first 2 are enantiomers. They have the same physical properties. The only difference between them is alpha. This is plus 12, this is minus 12. Now for the second one, which is the meso one, alpha is 0, which means that this compound is optically inactive, and that's expected because this compound is achiral, is not chiral, so it does not interact with a plane polarized light, and we call it optically inactive. So remember, meso compounds are usually optically inactive. Now sometimes we have to look to stereochemistry in reactions. For example, remember when we add HBr or HX in general to a double bond. Now there is a possibility of forming a chiral compound as a product. Now what we expect as a product, based on the mechanism of adding HBr, remember that the mechanism first go in 2 steps. The first step, adding hydrogen to the double bond forming carbocation, and then later Br minus attack. And now when we form carbocation is a flat, it's planar, it's sp2 carbon. So now the Br minus has identical possibility to come from the rear side or the front side, from the top or from the bottom. So because of this, we expect to form both R and S, and the amount of them are equal exactly. And this, we will have a mixture of both of them, both enantiomers. This kind of mixture is called Racemic mixture. It's a mixture of 2 compounds with the same amount. These 2 compounds are enantiomers, so they cancel each other concerning the optical activity. And this mixture is actually optically active. And you can see how why we form both of them in equal quantity S and R, because we have this intermediate, so the Br minus can come from front or come from the rear side with equal chances. So we get both of these with equal quantities, 50-50 or 1-to-1. Another possibility of having different stereoisomer, you can see here, is different than the previous example, that we have already chiral center here. So if this carbon is R or S, now when we add HBr, there is a possibility of forming S or forming R. So now we'll have R, R, or RS. And now that the products here are not racemic mixture, because we're getting the stereomers, not enantiomers. And because the stereomers have different physical and chemical properties, now we can separate them. So remember, when we add or form a product that has a new chiral centers, but we already have a chiral center in the original compound, we don't form racemic mixture. We form the stereomers that can be separated because they have different chemical and physical properties. As you see in this example. Actually, we use this method to separate enantiomers from racemic mixture. In the racemic mixture, we have both R and S. So if we react them with pure R or pure S, of course, now we get R interact with R, so we get RR, and R interact with the enantiomer S, and we get RS. Now we have a mixture of diastereomers instead of mixture of enantiomers, and now we can separate them because they have different chemical and physical properties. Let's review what we already have in stereoisomers in general. We have three kinds of stereoisomers. We have enantiomers or diastereomers, where we have a chiral center and or centers, and they could be mirror images, they are enantiomers. Not mirror images, they are diastereomers. And we have the cis and trans or Z and E stereoisomers also. And since the cis and trans or Z and E are not mirror images, so we also consider them as diastereomers. The different kind of stereoisomers are conformations, which we had before, and these are called staggered and eclipsed. By this we finish this chapter, and we will I hope you will study it, and if you have any question, you can ask me through the e-learning.